Okay, it's 11 a.m. So let's start with my talk, Adopting Java for the Serverless World. And I will be talking mainly about AWS applications, AWS Cloud, but there are similar concepts also in other cloud providers. So who of you has already experience with AWS as a cloud provider? Okay, more or less half of you. And who has experimented with serverless? Okay, mainly the same amount of people. So who of you are Java developers or have Java background? Okay, most of you. Okay, then I think that's very fine precondition. So let's start. Yeah, my name is Vadym. I'm Ukrainian native, have Russian wife, but let's not talk about this that stuff. I will need more than 1 hour. But anyway, I have these two passions, Java and AWS Cloud, mainly serverless, and I'm one of the co-organizers of Java user group Bonn, and I live in Bonn, and I'm AWS community builder in the serverless category. So kind of that's my passion and also obligation, kind of, to talk about this. So you can contact me via Twitter, LinkedIn. I'm very active there. So I mainly give this talk already for 3 years, adjusting it because there are exciting things happening around all that stuff. So there will be also lots of new information. So only several words about the company. Iplabs, probably unknown company, but we are a 100% subsidiary of the Fujifilm in Europe, based in Düsseldorf, Germany, and we provide software for creating and purchasing of the photo products, calendars, photo book of the year, everywhere where you can print the photo mainly. So in the last 4 years, we shut down all our data centers. We are completely on AWS, and we try to do the all new stuff with serverless first, at least first, and then if we run into some issues, we go to containers and also to EC2 instances, all that stuff. So lots of experiences with traditional, but also with serverless architectures. I also started as a developer, as a Java developer, 98. So it reveals how old I am currently. And now we also, the whole company developed backend with the Java, and then we struggled kind of with adopting serverless with Java, and many things. My personal researches, we also adopted TypeScript and so on for serverless application, because 4 years ago we could not wait for all that improvement. So now we have that mixed situation using different programming languages with serverless. So let's start to set the scene where we are currently. So let's start with the Java popularity, and it's more or less Java conference. And yeah, you see, depending on the source and how they calculate this number of job postings, GitHub repositories, commits, you will see in any statistic, Java will be between place 1 and 3. That's more or less undependent on this. And if we will go into AWS and serverless, AWS is a cloud provider, is a clear leader in most categories. This is infrastructure as a code, but there are also others. So this is since years the kind of a gap till Microsoft and Google, and then after this is nobody currently, more or less. And we will see that many organizations adopting serverless in some kind of stuff. It's not without challenges, and it's not the general talk about serverless. Of course, it's microservices architectures have their challenges, distributed systems, and also all that, but there are also advantages, and especially companies who are scaling in terms of teams and so on, they try to adopt some kind of microservices architecture. And if we see, it's a kind of a bit outdated statistic, but Lambda, which is in the core of AWS, function as a service, the number of invocation increased, yeah, because people now kind of adopt these technologies. But if we will look into the life of Java developer, especially on AWS serverless, we will see that kind of picture. So probably nobody would like to talk about Java 8. It was supported for Lambda with the Coreta. On Coreta is similar offering like Adopt OpenJDK, but from the AWS side. So they support even Java 8 until 2026 for good or bad. Even we have Java 8, it's not very easy to leave that path, so it's good to have it, but also, yeah, has the challenges. Coreta Java 11 was supported on Lambda since 2019, and it took 4 years for Java 17, the next long-term version to be supported on AWS, and it happened literally last month. So if they didn't do this, I would stay here and present you that very sad statistics that they don't even support Java 17, but now they are supporting, and there were some preconditions which led to this delay. So I currently quite convinced that if Java 21 will be released, it will not take too long for AWS to support it on the Lambda. Maximal 1 year and not like 3 that we waited for Java 17. And of course, they support only long-term versions for Lambda as a managed runtime. So there will be nothing in between, no Java 18, 19, something like this. So they backport all security performance stuff into these long-term versions. So what we see in Java is a very fast and mature programming language with a really amazing community. So lots of people here, lots of conferences. I don't know about any other programming language with that kind of community. But if we will look into serverless adoption for Java, we will mainly see something like this. Yeah, you see Java more or less something between 5 and 10%, and clear winner Python and then Node.js or JavaScript derivatives. It was from the beginning, I think, Java starting to close this gap, but it's still 1%, as a 1-digit percentage. So it's clearly not the situation that we have outside of the serverless world. It's Kubernetes and all that stuff. So the main question is why? Yeah, we have people, they have knowledge, there are emerging technologies, people would love to use cloud for certain purposes. So what are these things? So there are mainly 2 cold start times, also known as the latencies in the end, but also memory footprint, which also kind of factor of the costs. So let's start with kind of, not everybody may be familiar how to write Lambda function, where we kind of write the business logic in Java. So there are mainly, so you simply create Java function, then you select the runtime. Now you just selected Java 17 for, because it now has been released. You can select the architecture, ARM, or default one is x86. And then you have to select the memory. That's the only one thing that you can kind of adjust. And this is something between 128 megabytes until 10 gigabytes. And the CPU will be adjusted proportionally to the memory. And you will get the complete CPU, one CPU core if you have selected 1.8 gigabytes of memory. So if you select less, then you will get fraction of CPU. That will become important for some other stuff. So in terms how to write Java functions, there are more or less 2 flavors how to do this. On the left side, you have more or less the dependency to AWS SDK. You see this context request handler, and you have to implement only one function, this handle request. And on the right side is poor Java 8 functional style that you don't have this dependency. And you have this apply method. What's the difference more or less with using the left side? So the AWS SDK, you get this context, Lambda context object, and you can then derive the logger. And so all this is the last method to call get logger below. And you can also just print out how much time do you get until the function is expired. So maximal 15 minutes, but you can also set something lower, which will make sense probably if it's a public API, than several seconds. So it's about, I use AWS SDK more or less for this. The second thing which is important is price model. To understand the price model, you have more or less 2 tiers. This is the request tier and the duration memory tier, I would say. So the request tier is simple. It's independent on the programming language itself. So for 1 million requests, so 1 million calls of the Lambda functions, you will pay $20. More interesting is this duration memory tier. You see this price, it depends on the architecture. This is what you pay for if you select 1 gigabyte of memory and execute the function for 1 second. This is quite the price that you pay. It also depends on the architecture. ARM is 25% cheaper. You have to test if it will be quicker. It will also play a role. But more or less, that's the parameter. If you select, or if your function runs half of the second, you will pay the half of what I showed you. So it will be calculated proportionally. So this is one example. You have 1 million requests and you have this x86 architecture, you have half of the gig memory, and we will assume that each Lambda invocation takes equally 200 milliseconds, which of course cannot be true. Then you will pay $20 for the request tier and $67 for the memory duration tier, just to give you a grasp how that works. So let's start and come back. This were kind of more or less basics to understand how the things are set up in AWS, so or how this priced and how the things can be written. So the first challenge is this cold start, which is kind of one of the main stuff which prohibits more or less the adoption. And it's important to understand that we are talking Lambda is the function, so it's function as a service. So the container executing the function can only execute one function in parallel. So it's not scales like a Tomcat. So execution, then the container is returned back, more or less like a connection in the data source. Use it and then back. So that's very important that you will need so many containers, so many functions you would like to call in parallel. Yeah, and then you will run into the situation, for example, for the first invocation, there is no container. Yeah, you deployed new function, there's nothing up. Yeah, and then this is kind of stuff that needs to be prepared. Yeah, and this is this life cycle there. There's the whole runtime of AWS looks if there are 3 containers. Yeah, if we need more containers, because we now have 9 warm containers, but 10 requests in parallel, so 1 is missing. It needs to be started. So how it works, that's more or less what's the container. This is MicroVM, it's not Kubernetes. The AWS wrote its own firecracker VM for this purpose. And this VM, then Lambda will be started, and in case we selected Java as a managed runtime, then this JVM will be started, then Java runtime loads and initializes everything around, more or less, to execute this Lambda function with this handle request method or apply method, and the first static initializer block is executed. Yeah, like everything. Yeah? And first of all, the code of the function needs to be downloaded. I forgot it. It's placed on S3. So this is the first step, download the code. Then the execution environment with JVM will be started. And then this init phase with the static initializer block will be executed. These first 3 steps are kind of these cold starts. And the fourth one is this execution of the business logic within this handler, request handler function or apply function. Only this business logic is the warm start, and everything around this is a cold start, and it will be needed if the new container should be started. The one thing that is also important is this in this init phase with the static initializer block, you will receive the full CPU access for 10 seconds. Even if you selected half of the gigabyte memory for your function, it will give you 1/4 of complete CPU cycle, because the complete only will be for 1.8 gigabytes. For this static initializer block, you will receive the full CPU access for free for managed runtime for Java 11, 17. There are also others we'll be talking. So this is kind of hint we can speed up things there. If we select less memory, then having the full CPU cycle will allow us to speed up things outside of the function. So in the static initializer block itself. Yeah, that's the last thing. That's the warm invocation, more or less, and the Lambda calls this handler method. So let's assume we don't know any best practices, nothing, and we wrote simple serverless application on AWS where we have API gateway in front to receive the request. We have some Lambda functions, and we store the data into the DynamoDB NoSQL database. This is a typical serverless application. We have similar things like this because we store our products, the serverless stuff. So we have the tool to create products, photo products, and then do the stuff, them adjust prices. So all the stuff is serverless. So this architecture is more or less what we are also having. And if we will look into the cold start times with the Java 11, you will see these huge values. Yeah, even with the pure Java function, without any usage of the frameworks, you will run into some kind of, and this only the cold start, so the method execution will also come on top. And then you see, especially Spring Boot, based on reflection and all that stuff, then the results are quite disappointing on that. And of course, it's, if you have asynchronous application, you can say, okay, I can live with that. Nobody waiting for me. But if you have public facing applications, so nobody will wait, yeah, because you have to add at least probably 1 second for API gateway to receive the request and for your business logic to apply and the client to render the results. So you will end up with the cold starts that may be insane. And these are kind of even best case values. I will show you some optimization techniques. My first cold start was around 17 seconds, something like this. I didn't know anything. Where I wrote my first function, which stored something into DynamoDB 4 or 5 years ago without any best practices. The results were kind of disappointing, but the application was asynchronous, so it didn't bother too much. But of course, it raised questions how you can use this for public-facing application. Maybe most applications are kind of public-facing. So let's start with the best practices, how we can at least reduce it without applying all other techniques like GraalVM. We will be talking about this. So first of all, as you saw, the first step in the cold start phase is to download the code from S3. So the less you have in your code, less dependencies, then it's obvious will be quicker to download. So think about this, how you bundle the stuff. Sometimes if you use a server application like Tomcat, we don't think, yeah, one dependency more, and then it loads 20 others. It doesn't bother us. The application starts, take 1 second more. For Native and Tomcat, it doesn't do huge damage if the container leaves or the application leaves for weeks. But for the serverless world, it should be quick. So use only the dependencies that you need. With AWS SDK version 2.0, you have the possibility to shrink this. With the older versions, it wasn't possible, so all dependencies were loaded, and of course, it simply takes time. So if you use some clients, like in my case, it's Amazon DynamoDB client, you can create this client without these 2 lines in between, which are blue and red, because the region where you deploy, AWS can extract it for you. You know where you deploy in the runtime. They also, with the credentials, they have some kind of credential chain to look for the credentials to authorize the call, similar to filter logic in servlets, just with the chain. But you perfectly know where you deploy. So you can provide it statically. It will save you up to 700 milliseconds if you provide this. You know, and it's 2 additional lines of code will save you a lot of time, or at least. That's important. So this is also if we have the situation that we need kind of a HTTP client because we would like to do outside call. Yeah, the situation is with the Apache HTTP client, NetNeo HTTP client, they are for the long-living application world. They use heavily caching in memory and all this stuff for short-living Lambda application. These are not very well. So you will that will end up 2 seconds or something like this. AWS released their own asynchronous client several months ago. It was 3 years in preview, which is also insane. But anyway, as you see, it reduced a lot. I tested with it with just 1 or 2 seconds less call start time if you would like to do some or initialize this asynchronous client. But this has a kind of impact that if you use asynchronous HTTP client, you have to use, for example, also asynchronous DynamoDB client API. So all that APIs for S3 communication, SQS, if you use the tools for the services of AWS, you have the choice between asynchronous and synchronous and asynchronous API. In case your HTTP client is asynchronous, then you have no choice. And it's matter of taste to do it for you or not, but this is kind of then the implication, which is kind of logical. Then everything becomes asynchronous until the front end. Yeah, this is how to initialize it. So you can look into this. It's in this case, I communicate with S3 client, and I use this asynchronous S3 client passing this AWS own HTTP client. Another stuff, we need to retest it for Java 17, but this was also what I told you, that the cold starts was also kind of depends on the package size that we deploy, and mainly it's a zip that we provide with the business logic. Lots of graphs, but mainly what you will see here, the bigger the graph is, the bigger is the cold start time. And currently there is no correlation that Java 11 was better than Java 8. And I will assume that with the Java 17 it will be the same. So it doesn't improve something by default, but the artifact size matters, so we need to pay attention. This is, once again, all these dependencies and all that stuff, so don't include what you don't use. So now we will also talk about other stuff. So as I told you, we have 10 seconds in the static initializer block for the stuff, and we need to think what logic to place here. For example, using DynamoDB client, S3 client, all this initialization logic should be placed in this static initializer block. There is no need to reinitialize the client with each Lambda invocation. It's a waste of time. So this logic should be put outside, and then it's with the one core that you will get, it will be even, it will be even better, and you also save on that. Now there will come optimization technique that the people will probably say, what the hell, it just makes my code unreadable, and it calls the method, this kind of technique calls priming. It will be useful in the end of the talk if we will be talking about SnapStart and CRaC. But here we need to think about sometimes what causes kind of time when we do some stuff. For example, if we do the first call to the DynamoDB, in DynamoDB, then this is kind of JSON that needs to be converted into the objects back and so on. What will happen there that this Jackson marshaller needs to be initialized, and it takes 1.5 seconds. This is one-time stuff. If you first load this JSON marshaller classes and then do this stuff, and if it happens in the handler function itself, it's okay, because it's only one time. For the next execution, it will not be loaded, but then you have less memory. So we should try to put this logic into the static initializer block, but the problem is we don't have kind of dynamics there. We don't know what IDs to call. So simply what we are doing here, we're faking some call to the DynamoDB in order for Jackson marshaller to be initialized in the static initializer block, where we have 10 seconds and more memory. And with that, we win something. Of course, it's a fake code. It may even return an error, but in the end, the Jackson marshaller are initialized. This technique is called priming. So you need to think, do you need that? And in case you have 2 GB of memory, probably it will be much quicker to do this in the function call itself, and not outside in the static initializer block. But the most functions have half of a gigabyte of memory, 1 GB of memory. So it's worth thinking about it. But it's not, I would say, not the cleanest technique. That's totally clear that it's kind of, will be very important for the CRaC, because then we will have other advantages of that stuff. So anyway, there is one more technique which probably everybody should apply. This is using the TAST compilation. So only, probably there is client and server compilation, C1, C2, and for long-living application, you have the advantages of server C2 application, because just-in-time compiler kicks in, does 10,000 invocations, optimizes, just useless for the Lambda world. Yeah, just you don't need to wait 10,000 times, because probably the container with Lambda will be released anyway for security reason. AWS does it anyway, one time in 1 or 2 hours at latest. So you will not have the advantages. Yeah, so they will release even the warm containers. So this is the technique that you can say, I will stop with the compiler, with the client compiler, with the C1. And this is also kind of, because all this just-in-time compilation, they use threads behind the scene, they use memory and all that stuff. So if you just say, I don't need this aggressive optimization, and for the serverless application, you don't need it, then you can provide this option and simply stop. But general best practices just to avoid reflection, runtime bytecode generation, proxying, dynamic class loading, and of course the people who are using Spring will say it's just in the core of that. So what should I do? Yeah, I cannot avoid this by default. There is of course Juice and other frameworks which don't use all that stuff, but generally they have at least frameworks that were created decade ago were all based on that stuff. Just use that stuff, and for long-living application it was okay. So now we'll come back to this. I will also show you some cost optimization techniques. Once again, this was request duration tier that we need to remember. So the question is here, what will happen if I will double the memory? It's cost factor. You pay for the memory. If I double it, what will happen? The situation is that you will get double as much CPU with the chances that the Lambda function will be executed quicker, probably even double as quick. Yeah, more CPU may lead to performance boost, which will also decrease the cost because double as quick, this is the duration. Yeah, memory duration. You increase memory, decrease duration. The price may be similar, but the function will be executed quicker. So then it's maybe the advantage. But the situation is kind of how to prove it. Yeah, or what memory configuration will be okay. And there is this power tuning tool, which is open source from AWS people themselves, where you can use step function. This is kind of state machine. There you can say, this is my function. I will try to give some memory settings to try to figure out the best match for price performance stuff. And this is how the output will look like. So you see the duration and you see the pricing, and there will be somewhere kind of sweet spot where you say it doesn't make any sense to increase memory because I will not have any advantages of the speed. I pay more, and then the execution time is not reducing anymore significantly. This was the old graphics. Now we have two architectures. Also ARM is possible. Now you have more dimension to decide. Yeah, not the architecture, you know, the ARM architecture is 25% cheaper, but you will need to test how much time does it take to execute, because if it takes more, then you don't have any advantages, and it depends on your application mainly. Even if AWS advocates it will be always quicker, I know that it's kind of trade-off. Yeah, and there is also one tool in the AWS world itself. The name is AWS Compute Optimizer. It's even free, but it works a bit differently. You need to deploy your Lambda function, run it, I would say 2 weeks in production, they will generate insights. So here's the insight, you can reduce the memory and you can reduce the price. So this tool is also for EC2 instances and so on, but it also can give you insights on your Lambda. But the difference between the first tool is you can do it in advanced calculation. Here you need to wait a bit to these insights to be generated, because they calculate the real usage and not some fake invocations, more or less, in testing mode. So it's up to you, you can use even both. So now you saw that that situation with the pricing, how to just to thinking how to decrease it, and you saw the situation with the cold start, which is kind of insane for several use cases. Now let's see how to decrease that stuff, or what options are there, and all options have its own price. So probably that's not the talk about GraalVM. Everybody knows what it is. After 5 or 6 years, should be obvious. What is interesting for us is the substrate VM, which is kind of optional and on top on the GraalVM architecture. And what it gives us is it gives us ahead of time compilation. Yeah, so you basically need to say what classes, fields, methods are used in your application, and they are reachable more or less, and then the native image will be built for this. Native image for your operating system. So all three are supported: Linux, Windows, and Mac. And the situation is, of course, the native image only packages what is reachable, so there are no dependencies that are not used that will be bundled. And of course, it's also pre-compilated for the native machine. And of course, it should start quicker, obviously. Yeah, that's kind of in the core of ahead of time compilation. The problem is, the challenge is, GraalVM is not Java. Yeah, it's independent GraalVM, and native image is kind of the tool installed on top of this. And if you go and would like to deploy your Lambda function, you will not find GraalVM. You can only find Java managed runtime. So the question is how to deploy this on AWS, for example. And AWS gives you the possibility to provide custom runtime. And this is the possibility to provide this native image with some cost, but this is kind of that you can build this runtime, and provided the situation is they only support Linux. So this is the first one, you need to build this on Linux. And there is the format, like more or less what we deploy should be function zip, and in the root of this function zip there should be this native image, Linux native image generated by GraalVM native image, and then you can provide it as a custom runtime. Generally, what is good in GraalVM, they give you the choice between just-in-time compilation and ahead-of-time compilation, and these are the trade-offs. And you see just-in-time compilation is optimized for peak throughput, reduced latency, and more or less reduced latency, which is for long-living application, and ahead-of-time compilation is more suited for startup speed, low memory, and low packaging. So this kind of ahead-of-time compilation is more or less for serverless world. I will only briefly talk about, of course, we value the productivity, and that's why many of us are accustomed to use some framework on top of that. Who of you use Spring? Okay, yeah, logical. So the people don't want to give up this productivity stuff. More or less, the situation was, of course, that the Spring boot, as I told you, was developed with some other preconditions. But of course, if the problem arises, then there are solutions. And of course, this Quarkus and Micronaut, these independent libraries, were aimed at kind of creating, these libraries are more or less designed from the ground up with some other preconditions without using all these reflections and so on. I don't know why Quarkus is called Kubernetes native. If you can deploy it on AWS Cloud, this is probably some selling buzzwords, but anyway, you can use that in Kubernetes, in the cloud, on premise anyway. And Spring Native, yeah, this is kind of the project based on Spring, just to enable GraalVM native image underneath. So it took, I think, 2 years for Spring developer, for Spring, yeah, just to refactor the basic behind this to enable that stuff. But more or less, the principles of all that frameworks are the same. They use as little reflection as possible to enable this native image to work. No runtime generation. They try to process annotation at compile time. So everything that can be shifted to compile time will be shifted. Of course, that has the trade-off that compilation takes longer, and it breaks a bit developer experience. And of course, yeah, the goals are more or less to increase developer productivity. But of course, yeah, with kind of different trade-offs. There are also other stuff like Micronaut supports AOT in the compile time, so you can even gain performance, more performance. So I would say even less cold start, but you have to test if this AOT is something for you. So steps to deploy are simply you can use the framework of your choice, and on top of that you need GraalVM and native image. They all support Maven or Gradle, and you need some kind of tool for infrastructure as code for serverless applications. You can use SAM, or CloudFormation if you would like, anything. And in the end, you will build this Linux executable using the plugins of Maven or Gradle, and then you have to deploy it as this function zip into AWS as a custom runtime. I will only show you one example from Micronaut framework. These frameworks they're kind of similar. Micronaut is a bit different. They don't support standards, so this is their own development, but more or less people accustomed to using Spring will recognize the style. Yeah, you have these controllers, you have get and post methods. They come all from Micronaut package. Micronaut even supports Java Spring annotations, so you can use Spring and then use annotation processor and the compile time to convert the stuff. The same is true for Quarkus. So for the people, just if they say I'm quite accustomed with the Spring framework, they don't need to change. And you see this, there is nothing about AWS in this controller, no dependency, nothing is here. The whole magic will come into the dependencies. Yeah, you see this Micronaut function, AWS custom runtime dependency that will do the whole magic for you. Yeah, you have your pure Java applications, and you see then the Maven, let's say how you call this with Maven. This is the packaging native image, and you say that runtime is Lambda, and with that you can simply switch if you would like to deploy to Azure and others. That's this magic will also happen only in the POM XML. So your business logic is can be cloud agnostic, which is kind of cool. So I will not show you Spring Boot or Quarkus. They are simply the same, different companies, a bit different focuses. For Microsoft is more or less kind of the main developer is Graham Rocher, who is well known for Grails. He joined Oracle. AWS also is in advisory boards, so maybe that's a sign that AWS more supports Micronaut, and Quarkus is more from IBM Red Hat perspective, but similar frameworks with the similar goals. What I wanted to show you is that this were the cold start times without using GraalVM. This is for the same application using GraalVM native image and custom runtime. Your application may be a bit different, but what you see, you are getting below 1 second, and you are approximately going to the stuff that Python and Node.js provide you. With GraalVM, you have kind of library of frameworks that are supported more or less GraalVM ready, because they don't use reflection and so on, so you don't run into some problems in the runtime. Yeah, because it's always the fear with the head of time compilation that some call triggers in that does some reflection, and you didn't package the classes. Yeah, that's why many libraries need to be kind of refactored for this, and GraalVM has this kind of information they test, and they give you kind of insurance. If you use that, then everything is okay. More or less. So only several conclusions of GraalVM. Of course, they are really powerful, yeah, and they reduce this cold start times and memory footprint significantly, because ahead of time compilation does his job. But of course, it's not without challenges, and everything is a trade-off. And this AWS Lambda custom runtimes requires Linux, and not every developer develops on Linux. So the build phase and everything else is kind of on the other pipe or the other machine, so local testing will become difficult. And think of this building custom runtime, building native image. It requires 6 to 10 gigabytes of memory to build one native image. Let's imagine you have many microservices, many serverless applications, so you need to scale your CI/CD. For that. You cannot do this on the local machine, and you need to think how your CI/CD process kicks in, how much memory, how many machines in parallel. The build time is a factor. So for similar application, it can very basic native image takes 20 seconds, something like this. If you use other services like AWS services have dependencies, it could take 2 to 3 minutes. This is developer experience, yeah, to build this native image. And for custom runtime, you pay for initialization phase. It's not free. This 10 seconds maximal in the init code. It's not too much money, but it's only for free for managed runtimes like Java 11, 17, and so on. So I have 12 minutes left, and this is kind of another technique or another approach that received adoption in the last time, and this is the SnapStart. And it will be based on CRaC. And I was really surprised that AWS implemented this in the end of the last year. I thought that it will provide something like managed GraalVM to enable people who are using GraalVM to do it easier. That was my guess. But they did something completely different and surprising, and they announced the SnapStart. And what they are doing with the SnapStart, and it's based on CRaC, we will see, they snapshot, they do 2 snapshots. The first snapshot is the whole MicroVM snapshot. And the second snapshot is Java runtime snapshot. And they are doing this when you develop the function and deploy it. They are doing it in the deployed during the deployment. The first deployment, they invoke the function and make the snapshots. They store the snapshots. And then if you call the function for the first time, they restore the snapshots, what they are doing there. So only if SnapStart is enabled, of course. Yeah. So it's also trade-off. So the first deployment will take longer because, yeah, if the function has this SnapStart enabled, they do this. And this JVM snapshot, this is based on this CRaC, coordinated restore and checkpoint. And the idea behind this is that it takes, the situation is that all these compilers, they need to do the job. And in the end, after it, we are living in this container world or serverless world, that these containers come up and then they do all the same, more or less. And if you take the snapshot after their cold start, then the snapshot should be the same for more or less for each Java function, at least after the static initializer block, there is no dynamic. And this is kind of this idea to more or less to make the snapshots and then restore the snapshots very, very quickly. So this CRaC is based itself on this user Linux checkpoint restore in user space. This CRaC project, it's only supported on Linux since 2012. And the goal was more or less to support the migration of containers. So in this kind of the checkpoint, essentially the full context of the process is saved. So program counters, registers, text, memory, everything is saved, and then in the restore phase, everything will be loaded, and it's much quicker as to do this kind of, like JVM will do this. Of course, you have their challenges like open files, network connections, all the stuff. If you will try to store and to make the snapshot with the open connection, there you need probably to reset connection if you restore the phase. And of course, there are some system clocks and some random stuff that they need to pay attention. But I would say in the most applications don't do something like this, like open connection in the static initializer block. So why should you do this? So normally it's not the case. And this is the statistics from the people who, and it's the Azul people, probably you know JVM implementation Azul. They are kind of behind this open source project, and they kind of measured what does it take for the first, more or less for the first operation with CRaC and without CRaC. Yeah, and it takes much less time if you just store and then restore the stuff. And that was what AWS did. Kind of the SnapStart is more or less managed CRaC plus VM snapshot, and you can enable it on the function itself. You need to do this on per function base. It's optional. It's up to you. This is AWS SAM, or you can use other tool for infrastructure as a code. Then up to you. And if you enable this, then the next deployment will kick in this process. Then during the deployment, the function invocation will be done and then snapshotted. And in the case you then call the function in production, you will see the snapshot restore in the logs. So the question is, what will it bring? So now let's see with SnapStart and without SnapStart. Below is without. You see it's a huge improvement. We are not there with the GraalVM. With this first iteration, but it's at least even for Spring, you see it's just really, really big step down, only for enable SnapStart, more or less. Yeah, we don't need to do anything. We don't need to scale CI/CD for that. Everything else is done on AWS side during the deployment. What we can do now is, you probably remember this priming, this ugly code in the static initializer block. We can use that here as well. And CRaC supports this by providing resource interface. It's optional. If you do this, then you can implement before checkpoint. So what you do before the snapshot is taken, and there is also after restore, optionally also in case the restore is done. And before checkpoint is also a good place to do this ugly priming. to warm up all these jacks and marshalls and all that stuff that can make time. It can take time. And the situation is that this priming will take effect during the deployment before snapshot. So it's not taking something from production. It adds probably several hundred milliseconds for the deployment time itself, but it's only once, you don't deploy too much. So this priming leads to much more effect with CRaC itself. Yeah, because it's not about memory. It always makes sense if you think that you can speed up things, load classes, yeah, even in memory, that are only loaded during the invocation, not during the static initializer block, then it's a good things to go. And Micronaut supports it only to show you this. They provide their own CRaC ODAT resource, but the logic is the same. There are the same two methods before checkpoint and after before checkpoint and after restore, and I do this DynamoDB call to do this. And with the priming, now you see the things becoming better. At least in my case with DynamoDB, because I know this Jackson stuff takes time. Now you see we are just going below 1 second, even using the frameworks. The Spring is a bit different, yeah, but with Micronaut and Quarkus, I could achieve these values by doing the priming. Now, once again, don't look into this. It's ugly again, and it's even more ugly. I wanted to test how further I can do something with priming, at least with the frameworks, because using frameworks on top of Lambda, they have costs, because you have the Lambda, which then translates something into the Micronaut programming model, these annotations, the same stuff. So I wanted to do this priming call from Lambda just to warm up all this translation logic between Lambda and Micronaut programming model. And what I did here in the last method, I simply called within the priming more or less Micronaut controller. Yeah, it's ugly, I know, but I was wondering, can I bring the cold start even further by warming up all these Micronaut classes that will kick in during the first invocation. And now I more or less receive the same value as the GraalVM. It's ugly, I totally know, and I know that AWS is now kind of working on more or less open source project that will do this out of the box. They know what to warm up, depending on what services you use, that you don't need to write this priming code and even basic priming code. So they will provide some stuff behind the scene that at least your code looks good, but but they will figure out depending on what you are using, how to do the stuff. But generally, it's very young technology, and you see how things are possible. There is one challenge. If you measure this cold start, and CloudWatch shows you, AWS, they now confirmed they have some engineering problem. They don't show all the cold start within the CloudWatch metrics. There are several hundred milliseconds that are currently happening that are not shown. And we figured this out, me and several persons, because we measured the end-to-end latency from receiving the request and then sending it back, and figure out that in normal case it was bigger as we expected. AWS is working on reducing that stuff that is not shown, but generally these are end-to-end latencies with heavy priming. You see more or less we are behind 1 second for P50 in each case, but also outside. So we are kind of getting better, and everything below 1 second for the cold start, and you don't have all the time the cold start, so it's maybe 1% or less. It becomes now it becomes accessible. Nevertheless, also SnapStart has some limitations. It now supports 11 and 17, which is good. It supports only Java, which is, for us, it's okay. We are Java people. Deployment of this function where the SnapStart is enabled also takes 2.5 minutes, because this snapshotting, they are doing this in layers, and storing these layers, it takes time. Yeah, but if you deploy 10 Lambda functions, then they will be deployed in parallel, so you will not have too much penalty, only deploying many of them. Yeah, and SnapStart has some limitation. Provision concurrency, if you use it, is not supported. ARM architecture is not supported, only x86 currently. If you use NFS, Amazon Elastic File System, it's also not supported. You cannot mount it. You can only use S3. And ephemeral storage is only half of the gig. So kind of other trade-off. So that's kind of these two options. I don't want to compare it myself. So my opinion is SnapStart is young enough, but it becomes mature. Of course, 6 years of GraalVM experience, it's something different, so it becomes mature. I only know that the people not always comfortable using GraalVM because they fear some effects in production, which can be kicked in by ahead of time compilation. I think this barrier should be reduced by providing some tests on something like this in advance that can be run, because not everybody can build images, native images on the local machine. But on the other hand, there is also a lot of magic with this CRaC, with doing snapshotting and restoring. There are a lot of things that can go wrong with that as well, more or less. Yeah, something else can be restored, that the values can, in theory, be lost. Only why we keeping just-in-time compiler doesn't always mean that everything is fine. But nevertheless, I think it's always okay to have a choice. Yeah, now you have with GraalVM native image the choice. If you are on AWS, you have this managed SnapStart on Lambda function based on CRaC. And I think this makes Java more accessible for the people try serverless applications now without fearing having this huge cold start and memory assumption. So I'm out of time. I would say thank you very much for listening. I hope you could take something with you and try things out. Yeah.